Hello, students. Well, as we mentioned yesterday, we are going to be focusing on our dirtiest topic of the year this week. Yes, this is a dirty topic, but we must discuss it. We are talking this week about, about soil. There we go. About soil. So, yesterday I introduced you to some basic concepts regarding soil. Today we're going to explore some words in a little bit more detail and then prepare us for our lab activity, which is going to be a dirty experiment on Thursday, but we will prepare ourselves for that. So let's get our notebooks opened and let's start recording some information about soil. Yesterday, we talked briefly about how soil and dirt are not the same thing. Soil is more than just dirt, as we will continue to explore this week. But we can define soil basically as a mixture of weathered rock and humus. Humus is that organic material that exists from the decomposition of plant matter and animal material, and that decomposed organic material adds very important nutrients to the weathered rock in order for soil to be classified as soil and be able to grow plants in it. So soil, a mixture of weathered rock and humus. And as we've mentioned more than once, soil is capable of growing plants. So be careful. Be careful when you're looking outside and you see a pile of material and just call it a pile of dirt. Well, it may be a pile of dirt, but if there are plants growing on it, it's not dirt. It's soil. Make sure you know the distinction between dirt and soil. Dirt can't grow plants. Soil can grow plants. In fact, that sounds like a good quiz question for this week. So soil is capable of growing plants. Now, here's some terms for us to remember throughout the week. How many of you have ever watched the Flintstones? Flintstones, meet the Flintstones. They're a yabba-dabba-doo family. They come from the town of Bedrock. And bedrock is the name of the layer of rock that is at the bottom of soil. And bedrock can be deeper in some areas than in other areas. There are plenty of areas nearby, like up at Jenny Jump Mountain, where the bedrock is right at the surface of the ground because there is no soil on top of it. Whereas, well, let's say here in the school grounds, we might dig down several feet before we reach bedrock. But bedrock, whether it's shallow or deep, is the layer of rock beneath the soil. And on this picture here, we've got the topsoil, the subsoil, and at the very bottom, the bedrock. By the way, do you guys know who these characters are? Let me point to them and see if you know their names. Main character, his friend, main character's wife, his friend's wife. I grew up watching the Flintstones. I love Fred, Barney, Wilma, and Betty Rubble. Yeah. Okay, let's move on. So back to this word humus. It is not the same thing as hummus. Hummus is a plant that some people eat. I don't find it very appetizing myself. It tastes like moss, in my opinion. But humus includes the dead plants and animals that can be found in soil. It is the organic material. Organic refers to life, living things, or things that once were alive. So plants and animals that die, they're organic because they were once alive. But whenever a living thing like a plant or an animal dies, it undergoes decomposition, and the various minerals that make up those organisms are then restored and returned to the soil in the form of humus. Now, there's another term here called residual soil. And the residual soil is similar to the parent bedrock. Let's see if I can give you an example. We saw in a video yesterday about how different kinds of rocks produce different kinds of soils. And soils can be of different colors. I love driving through our great state of New Jersey, from the highlands up here where we live down to the shore each summer. And if you really pay attention like I do, because I love rocks and minerals and things like that in the outdoors, if you look at the soil and the dirt on the roadsides as you travel from north to south in New Jersey, you'll notice a different color with basically every county you travel through. From the darker soils in the north to in the middle part of the state, the soil seems red. That red is a result of the parent bedrock material, the red shales in which dinosaur fossils can be found. And then continuing to drive down to the shore region where the soil is actually much thinner and much lighter, like sand, because most of the residual soil is from quartzite, from basically sand decomposing. But the residual soil is similar to the parent bedrock. Now, here's another word: transported soil. Many of you live in homes that were built probably in the last generation or so. And some of you may even live in developments. And in developments, if you've ever seen one of these developments being built, they have to use big machinery like this in order to move the soil from one place to another to build the foundations for the homes and the roads, etc. And then they bring topsoil back so that you can have a garden or a lawn or front and backyard. Well, that soil was brought from somewhere else. If you recall, in our last topic, we talked about glacial erratics and how glacial erratics are rocks on top of formations, and it's so evident they just don't belong there because they were brought from somewhere else. Likewise with transported soil. I've spent a lot of time down the Jersey Shore, and if you've ever dug a hole down the Jersey Shore, it's just a lot of sand. There's not much topsoil. A lot of the topsoil down there has been brought in or transported from somewhere else. And so when a soil does not reflect the parent material underneath it, it's probably a transported soil. Now, transported soil can also occur through erosion. We mentioned the glacial erratic a moment ago, but water, wind, waves, glaciers, those agents of erosion we learned about last week, can have a major impact on moving soil from one place to another. You may recall last week when we talked about stream load and how rivers and streams, after a rainstorm, get this dark color of all of the sediment found within it. It's transporting it from one place to another. So erosion, deposition from last week, erosion from one place, deposition to another place, is a great mechanism by which soil can be transported from one place to another. All right, now here's some other terms. This is a term we're going to be getting into with our lab activity later this week, but it's called porosity. Porosity. I'm sure you've heard of porosity before. Maybe you've heard of clogged pores. At this point in your life, as you are beginning adolescence, you may have heard of that dreaded condition called clogged pores that can result in pimples. That's right. Well, what are pores? Pores are little holes. Our skin is very holy. We've got lots of openings in our skin that allows liquids and materials out of our body, like when we sweat, for instance. We also excrete or release other materials, various oils. And when sometimes those oils clog the pores, they can result in pimples, a plugged or clogged pore. What does that have to do with soil porosity? Well, the word porosity comes from the same word from pore. Porosity describes the empty spaces between soil particles, just like the pores in your skin are the empty spaces between skin cells. So, porosity describes the empty spaces between soil particles. And this is a really important point. As I'm talking here, you can probably see in the animation water dripping through the pores. And that's really important because soil porosity, those openings, are either going to be filled with air and or water. Like after a rainstorm, those empty spaces are going to be filled with water. Well, if you're a plant growing in soil and your roots go into the soil porosity is going to be really important to you because you're going to need to rely on that water to survive. And a soil with a higher porosity is going to enable you to draw upon water even long after a rainstorm has left an area. If you're in a soil with very low soil porosity, however, there may not be a lot of water left. So soil porosity, very important. Also important for if you are living in an area like many of you do here in this township, you might rely on a septic system. A septic system requires high porosity because whenever you drain a sink or you flush a toilet and that water goes into a septic system, you're going to want high porosity so that whatever is flushed down filters through the soil particles. If you have a soil with very low porosity, you're going to have to bring in a lot more soil and do a lot more excavation. And it's going to be a lot more expensive if you don't have the right type of soil. And speaking of the right type of soil, how do you know? Well, we can discuss something called soil texture. And we're going to be learning a lot more about soil texture in the lab this week. But the soil texture of a soil sample is based on the composition or what the soil is made out of. And more particularly, it's determined by the particle sizes in that soil sample. You see, not all soil is the same. If you play in a sandbox like ours here at the school, the sandbox has certain grain sizes to give it a certain texture. If you were to play around in our stream tables like we did last week, that soil has a different texture. If you play with clay, that has a different texture entirely. So, what are some of the different sized particles that exist in soil? Well, it varies from gravel to sand to silt to clay. So here's a great visual picture here describing the various sizes of the particles, and these are all magnified, by the way. If you look at our ruler at the bottom, from here to here is 1 millimeter. So gravel can be greater than 2 millimeters in size, sand smaller than that, silt really small, and well, clay is microscopic. So let's take this visual picture and put it into words. Clay. Clay are the smallest particles in soil. In fact, if you were to measure them with a small enough ruler, which would be tough to get, it would be less than 0.004 millimeters. In other words, clay particles are microscopic. You literally need a microscope to see the individual grains of clay. You cannot see clay with the unaided eye. You can feel it, you can play with it. I'm sure you've played around with clay, maybe in art class. But as far as seeing it in the soil, particle size wise, yeah, it's too small for us to see. Clay has very interesting properties, including the fact that when it gets wet, it's basically an impervious particle size. We saw this last unit when we learned about the infiltration of different particle sizes. And if you remember that lab that we did, the groups with the clay, the water just sat on it and never filtered down into the funnel because those tiny particles are an impervious layer. That brings us to the next one, which is silt. Silt can range in size from 0.004 millimeters, the largest size of clay, all the way up to, as if that's a big size, 0.0625 millimeters. Also super small, getting into the range where you might be able to detect the grains without a microscope, but still awfully small. But when you feel silt, silt feels silky smooth. At least I think so. Silt has a very cool texture to it. It's as smooth as, I would say, like baby powder, because the grain sizes are about the same as baby powder. All right, moving right along, we've now got sand, which varies tremendously in size from 0.0625 millimeters all the way up to 2 millimeters. And playing in the sandbox, we know what sand feels like. But again, there can be different granularities to sand, from fine sand to coarse sand. But here in this sand, you can see it looks like a deer print in the sand. Is probably on the bank of a stream nearby. You'd see footprints of deer that look like this. And that brings us up to gravel. Gravel are the largest particle sizes in a typical soil sample, and gravel ranges in size from 2 millimeters all the way up to 64 millimeters, which, if you do the math, is 6.4 centimeters. So gravel can vary tremendously in size as well. So we've got all of these different particle sizes, and based on the proportion of each, we can develop a totally different type of soil. Now, if your objective is to grow plants, like if you were a farmer, then you are certainly most interested in a soil type called a loam. A loam soil is ideal for crops, for growing plants. It is literally a perfect blend of particle sizes for growing plants. It has enough silt, sand, clay, gravel to give the ideal porosity and texture that most plants love. And so loam soils are the ideal soil for farmers. Now, how do you know whether a soil is good or not? Well, farmers can determine whether a soil is good or not probably just by looking at it, but certainly by picking it up and squeezing a handful of it. Squeezing a handful of soil tells a farmer intuitively, very accurately, in fact, just how much clay, silt, sand, and gravel is in that sample. And they would probably know very well how much of each component is in that soil and whether they would have to change that soil or amend that soil to bring in other particle sizes. But we're going to be working with something called a texture triangle. And again, this is something we'll be doing in the lab this week. We're going to be analyzing a sample of soil. And we'll be learning how to use this interesting three-sided graph called a texture triangle. And let me just point out a few things real quick on this texture triangle. On one side, we have the percentage of clay. On the other side, we have the percentage of silt. And on the bottom, we have the percentage of sand. And if you look at the numbers here on our graph, the clay goes from 0 to 100%, from bottom left to the upper center. The percent silt actually goes from 0 at the top all the way down to 100 in the lower right. And then the percent sand goes from 0 on the right to 100% on the left, which is why if your soil type is way over here, you've got a sandy soil. If you've got 100% clay, you've got a clayy soil. And if you've got a lot of silt, you've got a silty soil. Notice this colorful triangle, because based on the percentage of each, we have a different type of soil. So we're going to be analyzing a soil sample to find what percentage of it is clay, what percentage is silt, and what percentage is sand. And where the three lines come together, that will tell us what type of soil we have. And as I mentioned to you before, a farmer loves to have a loam soil, and you can see how that soil type is right in the middle of the soil texture triangle. So we're going to be doing a lot of things this week with different soil particle sizes. We're going to learn how to separate the particle sizes, and I think you're going to have fun doing that in the lab. We're going to actually separate from a sample the clay, silt, sand, and gravel, and it's a pretty cool way of doing it, so stay tuned on that. But we'll be using that information to help us determine what type of soil we're actually dealing with. But there's so much more to talk about and learn about soils. Tomorrow, we are going to be focusing on the soil horizon and the profile of a soil. And we're also going to be talking about factors that affect the type of soil. So we'll save all of that for tomorrow's lesson. So for now, I'm going to say bye-bye.